Welcome to another video in our course on stochastic processes. We now know about martingales. We heard about the optional stopping and the optional sampling theorem last time, and today we will use this knowledge in order to show two very important theorems, which are the first two martingale convergence results. So martingales converge in the first almost surely, and the second one in L1 under very mild conditions. Let's see.
So, Martingale convergence result. First video about this. We are starting with the so-called maximum inequality, which was proved by Dupe, who also invented all these martingales. The point about this maximum inequality is that we are doing something and we are computing something based on the supremum of xs, which means when we have a path or so of this submartingale, the supremum is the highest point that you have up to some time t. So t is here, and here is this supremum. And we're computing something about the supremum of the submartingale. And the nice thing is about all this, that the right-hand side, okay, it's an expectation, conditional, so on some set, that can be apparently bounded from above by this here. And the nice thing is that I'm doing something on the supremum here, and I bound this from above by the expectation of x at the latest time point here, so at xt. So for this here, I need no knowledge about all these paths, but I get a probability on these paths. That's one reason why martingales are so nice. Let's try to prove this using the optional sampling theorem. We are setting t, which is small t, maximum the entry of the stochastic process on the set lambda to infinity, which means that this supremum here is bigger than lambda. That's the same as this t here. So that's something with this t here is less than t, like this, less or equal than t. No, not equal. So like this here. So that's just the same. So we're computing something on this waiting time. And we are doing this using the optional sampling theorem. Apparently, capital T is bounded from above by small t. And we can use the optional sampling theorem, which tells us that this here is larger than x at the stopping time t. Yes, and I can split this up in the expectation of x capital T on the set where this supremum of xs is bigger than lambda for s less or equal to t, plus the other direction, x capital T, the supremum here of xs is less than or equal than lambda. And now I can bound this from below. So here sub xs is bigger or equal to lambda, which means x index capital T is bigger or equal than lambda times the probability of this set xs, like so, plus, well, if sub xs s less or equal than t is at most lambda, that means that x capital T equals x small t. because t has not occurred by time t. So this entry thing here has not occurred by time t. Like this. Xt on this set. So. And now all what I have to do is subtract this here from both sides, where I end up with this expectation on the other set here, sub xs less than lambda. Here I have exactly the right hand side. Wait. No. Here I have a typo. That must be smaller. Must be smaller in both cases. Subtracting this, so bigger or equal to stays, which is exactly this thing here. Okay, and from this to this inequality here, and that's easy because xt is always less or equal than the absolute value of xt. And we have already proved the maximum inequality. There is another version of this, which I have on this slide here, where the first thing, well, we already did that, because if p is at least 1, with xs also absolute value of xs to the power of p is a submartingale, and I can use this here on the submartingale xs to the power of p in order to derive this here. And there is another version of this where we do not compute something with the probability that this expectation the probability that the supremum is at least lambda, but with the expectation of the supremum here. And I can compute something, and again I'm connecting this supremum here, so which depends on the full path, and I'm connecting this to the expectation of the xt to the power of p at the latest time point. How to do this? We fix a k. So I'm not writing all this, I'm just explaining to you this now. We fix a k, and we want to compute this expectation here. xs minimum k to the power of p. I'm going to write that more in an advanced way. This integral here, when you do this, p times lambda to the p minus 1 has an antiderivative which is lambda to the power of p. I'm putting this here instead of the lambda, and I have exactly this here, which is the explanation for this equality. Of course, I can also say, well, I'm not integrating from 0 to the supreme here, I'm integrating from 0 to k, but I multiply this here with the indicator that lambda, which is the integrating variable here, is less than this maximum here. That's also easy. Now I can use Fubini and exchange the expectation in the integral to the effect that I have the expectation of an indicator, which is a probability. And for this probability, I already have something. I already have the first thing here. From the maximal inequality. Yes, so lambda times this, as we had here, lambda times this is less than or equal to this. I'm using this, I get lambda to the power p minus 2. And I just write what was written here. Okay, that's easy. Now I can perform the integral, because as you might recall, here's one. As you might recall, there's a formula for the expectation of something to the power of p minus 1 in this case. And it's exactly this formula here. I get this p from here, the p minus 1 from the integration, the xt from here, and the supreme as I did here. So then I'm using Hölle's inequality in order to distinguish here the xt and the supremum. I want to have this in two separate expectations. I can do that. I have a p minus 1 here, and here you have to do the arithmetics in order to come up with the right exponents in the Hölle inequality. So p minus 1 over p plus 1 over p equals 1. And that expectation here comes with the power 1, so that's an L1 norm. And here I have a p norm here and a q norm here, where q is p over p minus 1. And this here to the power of p divided by p minus 1, is that to the power of p. And that means we are done here. And now we can first we can divide by this here, which means on this side here we get something which is 1 minus p minus 1 over p, which is 1 over p. This here 1 over p. Yes. And this here stays, and then I do all this to the power of p. And then I have the same thing here and here. Once I let k go to infinity. And this here I have to do to the power of p, which is this here. And this to the power of p, which is this here. And I'm done with this proof. And with this, we can now come to the Martingale convergence results. And a basic notion here are so-called upcrossings. Here I made a figure. So an upcrossing is something, so you have to fix two numbers, for example, minus 20 and 10 here. And the first upcrossing between minus 20 and 10 is from here to here. So in this area here, I have an upcrossing between minus 20 and 10. Then nothing really very much happens until I first am below minus 20 again. And I have the second upcrossing here. Like this here. Here's the second upcrossing. And here's the third. And here is the fourth upcrossing. And UAB super index T here is the number of finished upcrossings between A and B and up to time t. And yeah, so here I define this formally here. So the SKs are the first times in the upcrossings, and they are done by time capital T and so on. And the following lemma is central to all what happens in the rest of this lecture, which is the upcrossing lemma, which bounds the expected number of upcrossings between A and B before time t by, well, again we have something as in the maximum inequality, so this number of upcrossings here, it depends on the full path. And what's written here only depends on the distribution of the martingale or submartingale at the end time point. Yeah. So in order to prove this, I say without loss of generality, I have that the stochastic process is never negative and A equals 0. So this thing here is without loss of generality 0, because if it's not 0, I can move the y-axis such that this A becomes 0. I'm defining a function or a process h where ht is, is the sum over all k, indicator sk less than or equal to t, less than or equal to tk, which means it jumps between 0 and 1, and it's 1 if I'm in such an upcrossing, and it's 0 otherwise. Then xtk minus xsk is at least b. So the upcrossings that I'm just considering are between a, which is 0, and b. So the difference is b. And well, sk is the first time after the last t comes on, so I'm below a, and here I'm again above b. So and the time, so the amount of increment you're doing is at least b, therefore. X is a submartingale, and the function h here is pre-visible. Which means that ht is ft minus 1 measurable, because by time t I know which of these things happened by time t minus 1. Because previsible, I can say that h times x is a martingale, and by time tk, I have a sum here over all k. I have a sum over all s, where this h is 1, from si plus 1 up to ti, xs minus xs minus 1. Well, the increment here is between xti and xsi, which is at most k times b, at least k times b. Yes. So this is true by time tk. This integral is at least k times b. So that's on the one hand side. And I also know that h times x here, that's a martingale or submartingale. And I can compute something. The expectation of xt, well, that's more, or that's at least the expectation of xt minus x0. I can split this up here to the expectation of, well, h times x by time t plus the expectation of 1 minus h times x by time t. So h is either 0 or 1, x is non-negative. Which means that this here is never smaller than 0. And I can bound this here from below by the expectation of h times x by time t. Sorry, no, that was the wrong argument. And the right argument here is that 1 minus h times x, well, x is a martingale, and that's also a martingale as a stochastic integral. It starts with 0, so the expectation must also be 0. And this here, by time tk, I have this here bounded from below by k times b, and k is the number of upcrossings up to that time point. And more generally, that's bigger or equal to less, that's at least b times the expected number of upcrossings between 0 and b by time t. And with this, I have already shown this upcrossing lemma. And now we can come to the first Martingale convergence theorem. And the main point is here to understand if I have a function, how can it be that this function has a finite number of upcrossings between any a's and any b's? Okay, for example, the function which diverges, that's one case where the number of upcrossings between any 2 points here is finite. That might be the case. But if it does not diverge, it's something else. How can it be that the number of upcrossings is finite for any 2 a's and b's? So for example, the number of upcrossings is finite between these two, which means, well, what can happen? It can be eventually stuck here, or it can be not stuck and be just somewhere else. But if it does not diverge, basically the only possibility is convergence, where you have a number of upcrossings is finite between any a and b here, it can converge. For example, that's basically the only thing that can happen. But of course, we have to be sure that the number of upcrossings between any a's and b's is finite. And for this, we have this thing here. Supremum of all t xt to the power plus is finite. Why do we have this? Because when we have this here, all these right-hand sides here will be not 0 and not infinity. It might be 0, but maybe they're not infinity. And if that's not infinity, all these upcrossings here are not infinity in expectation, and if they're not infinite in expectation, they're almost surely not infinite. I mean, of course, everything is only almost surely, and I have to still deal with a null set UABT equals infinity. So that's the space, so that's the set of paths where something is violated, which means the number of upcrossings is infinity, and that is a null set. Because we know that this random variable here has finite expectation. So it's almost truly finite. And on the complement of n, we have convergence, as we just argued. Nothing else than convergence can happen. X infinity equals lim inf xt, which equals lim sup xt. So we have convergence. And what else? The expectation of xt power of infinity. No. Expectation of x infinity plus. Yeah, so at time infinity, what's the positive part of x infinity? By phi 2, that's at most the supremum over all t, expectation of xt infinity, which is finite by assumption. And similar is the expectation of the negative part of x infinity. Yeah, that's at most, again by phi 2, lim inf expectation of xt minus which is lim inf and xt minus. I can compute this by using xt plus minus expectation of xt. Okay, the expectation of xt equals the expectation of, well, x0, not quite, but we have a submartingale, so I can bound it. So the expectation of xt is bigger than the expectation of x0, but I have a minus in front of this. So I have here at most supreme over all t expectation xt plus minus the expectation of x infinity, and this right hand side is finite because the first term is finite here by assumption. The second one is finite because x0 has finite expectation. And we've shown the first Martingale convergence result. And all what happens now are corollaries, more or less. First of all, well, we have here a submartingale and something is finite. The next result is we have a supermartingale, but if you have a supermartingale, minus x is a submartingale. So, and if you have a submartingale minus x and x is non-negative, minus x is not positive. And if x is not positive, this expectation here is 0 anyway. Then in this case, we have convergence immediately. That's this thing here, a non-negative supermartingale. Then we have almost sure convergence. And the proof is apply 1429 to minus x. That's the whole proof. Examples. Branching processes are a nice source of martingales which converge, as we'll just see. We had this branching process. Here zt plus 1 equals sum of I from 1 to zt xit. So xit is the number of offspring of the individual I in generation t. which then live in generation t plus 1. We already computed that z is a martingale if and only if the expectation of one of these x's here is 1. We also computed that zt divided by mu to the power of t is a martingale. That's also in on some previous slides. And that's here, of course, zt, that's a population number, which is not negative, which means for mu equal 1, z is a non-negative martingale. A non-negative martingale is a non-negative supermartingale, and converges by this result here. Yeah, so it converges to 0. Except this must be here 1430. So it converges to 0 because there's no other way it can converge. On the other hand, zt divided by mu to the power of t, it's also non-negative martingale and converges almost surely. So there's an z infinity such that zt divided by mu to the power of t also converges. So these are two simple applications of the last result. Now we come to the second martingale convergence result, which is a result which is a bit stronger in its conclusions because we have convergence not only almost surely but also in L1. And as you might remember, usually what one needs is uniform integrability for this. So if I already have almost true convergence, I need uniform integrability, usually. So x is a submartingale. The following are equivalent. Uniformly integrable, if they are uniformly integrable. In particular, this thing here is true, so the assumption of the first martingale convergence result. And then we have almost true convergence, and from the almost true convergence plus uniform integrability, we also have the L1 convergence. So that's okay. So from 1 to 3, that's okay. Next thing which we can conclude is from 2 to 1. If there exists x infinity such that this here is a martingale, submartingale, then x is uniformly integrable. Here I recall something from last semester. Where do we have it? Here. We had, if I have x in L1, that all conditional expectations of this thing here, that's a uniform integrable family. And if this here is a martingale, x infinity is this random variable such that all the conditional expectations are at most smaller, which means they're uniformly integrable. So from 2 to 1 we also have it, and we need from 3 to 2. From 3 to 2, and then we have it. Then we come all the way to equivalence. So I need this here, and I need, so I have L1 convergence, and I have to prove the submartingale property. First of all, if I have the expectation of xt given fs, s less or equal than t, minus the expectation of x infinity given fs, well, this here converges to 0. So the expectation of this here goes to 0. Because I can bound this here from above by the expectation of xt minus x infinity. But xt minus x infinity, by assumption, goes to 0 because I have the L1 convergence here. So this here is true. And what do we need to prove actually? I need to prove that the conditional expectation of x infinity given fs is at most xs. So that's what I must prove. And I'm doing this using the defining property of the conditional expectation. So I start with the conditional expectation of the conditional expectation of x infinity given fs on some set A, which is in fs. This here is, by what we just showed, the limit of t goes to infinity expectation of the conditional expectation of xt given fs, like this here. That converges. That also holds on the same A. Okay, and xt given fs, that's greater or equal than xs. And the same holds true that this here is xs on the set A. And that means that I have shown what I wanted to show, because it means that this thing here must be greater or equal than xs. Well, because A, you could just take the set where xs is bigger. A could be the set where xs is bigger than this thing here. That's in fs. You would still have this here. So on the set where xs is bigger than this here, this is bigger than this here. But on the set here, I have exactly the opposite, which means that must be 0. Xs is less or equal than x infinity given fs almost surely. And we have shown the second Martingale convergence result. So two things remain. First, another result here on LP bounded martingales. So the question is, how can it be that x is uniformly integrable? And one case is where x is LP bounded. And if x is LP bounded for some p bigger than 1, there exists some x infinity in LP such that I even have LP convergence here. And then xt to the power of p is uniformly integrable. Yeah, LP boundedness implies uniform integrability. So x is uniformly integrable, which means I can apply the last result here. So xt goes almost surely and in L1 to x infinity. Using now Dup's inequality, I have the following. I have the expectation of the supremum of xt to the power of p for all t here that's the limit by monotone convergence s less or equal to t. The limit of t goes to infinity, expectation supremum for all s less or equal than t, power of xs to the power of p. So that's increasing in t. I can bound it from above using Dup's inequality. Limit t goes to infinity. P divided by p minus 1 to the power of p, that's just some final number. Expectation of xt to the power of p. And it's LP bounded, which means the right hand side is bounded, so that's less than infinity. And that means that random variable here is bound is in L1 is in L1 and is apparently an upper bound for the process xt. And in this case, we have that the martingale, so xt to the power of p is uniformly integrable. So we have just shown xt to the power of p is uniformly integrable. And I can use the other result, and therefore I know also about LP convergence. Okay, we're almost done. Just one last example, again on branching processes. We had that this thing here is a martingale, but we want to see when this martingale is LP bounded or L2 bounded. And one thing is we can compute the second moment by using the quadratic variation of y. Okay, there is something, and we can then ask ourselves, when is this thing finite, or when does it have finite expectation? And the answer is if mu is bigger than 1, because then I can do something here. If mu is bigger than 1, then we will show that the variance is finite. And that means the martingale is L2 bounded. And, well, we can use the result. So convergence of yt to some y infinity not only is almost sure, but it's even in L2. Okay, so let's go through this first calculation here. Yeah, so we have to sum, so the sum here, these conditional variances. So here is the expectation what will happen, here is what actually happened, square. We have to sum this up for computing the quadratic variation, and here I have the I have used the formula for the quadratic variation, condition here on fs minus 1. So that's the conditional variance of this thing here given that s minus 1. And this conditional variance, so these things here are conditionally independent. So I can pull this out of the variance. I've set s minus 1 times the same variance, which is the variance of x1. So that's just the offspring distribution. It's the variance of the offspring distribution. Like this here, and the mu to the power of 2s, that's just here because I have this here in the denominator. And from this, we now see these L2 convergence, given that p is bigger than 1. So given that mu is bigger than 1. Okay, that's it for this video, and there will be some more applications on these Martingale convergence results in the next video. See you then.